Before I resume looking at the block diagram of the PIC16F684, I'd like to read a definition of what indirect addressing is. Indirect addressing in the context of the PIC16F684 microcontroller refers to a method of accessing memory locations indirectly through a register, rather than directly specifying the address in the instruction itself. This is particularly useful when dealing with data structures such as arrays, or when performing operations on a series of memory locations. The PIC16F684 uses the File Select Register, FSR, and the Indirect Data Memory Addressing Register, INDF, to achieve indirect addressing. Here's how it works. FSR, File Select Register. This is a special purpose register that holds the address of the data memory location to be accessed. Number 2, INDF, Indirect Data Memory Addressing Register. This is a pseudo register that does not exist as a physical register in the memory map. When you read from or write to the INDF register, it actually reads from or writes to the memory location pointed to by the FSR. Here is a step-by-step example of indirect addressing. Number 1, load the FSR with the address of the memory location you want to access. And here's some examples. Move LW 0x20. Load W with the address 0x20. Move WF FSR. Move W into FSR. Now FSR points to address 0x20. Number 2, access the memory location using INDF. Move F, INDF, W, move the value at the address pointed to by FSR into W. In this example, the FSR is first loaded with the address 0x20. Then, when you read from the INDF register, it actually reads from the memory location 0x20. If you write to INDF, it writes to the memory location 0x20. Key points. Indirect addressing allows you to access any address in the data memory without specifying the address directly in the instruction. It is useful for operations that need to iterate over a range of addresses, such as loops, processing arrays. The combination of FSR and INDF is essential for implementing indirect addressing in the PIC16F684. This method provides flexibility and efficiency in programming, especially for repetitive tasks involving data manipulation across multiple memory locations. Hi guys, it's really important that you subscribe. Yes, you. So go ahead and do that. Now please. Alright, so let's continue looking at the PIC16F684 block diagram. Let's take a look at the FSR register. In the PIC16F684 microcontroller, the file select register is a special function register that plays a crucial role in indirect addressing. The FSR is used to point to any location within the data memory, enabling the CPU to access data indirectly through a mechanism that involves the FSR and the INDF, Indirect Data Memory Addressing Register. Understanding the FSR in the block diagram. Location of FSR. The FSR is located within the special function register SFR place of the PIC16F684. It's a part of the microcontroller's register set specifically designed for indirect addressing. Functionality. Pointer to data memory. The primary function of the FSR is to hold the address of the data memory location that you want to access. This address can range from 0x00 to the maximum address of the data memory. Dynamic addressing. By changing the value in the FSR, you can dynamically access different memory locations without needing to change the instruction itself. This is particularly useful for loops and data structures like arrays. How FSR works with INDF. When you perform operations on the INDF register, the actual operation is performed on the memory location pointed to by the FSR. The INDF is a pseudo-register and does not have a physical address. Instead, it acts as a proxy for the address held in the FSR. Reading and writing using FSR and INDF. Reading. To read from a memory location indirectly, you load the address into the FSR and then read from the INDF register. Writing. To write to a memory location indirectly, you load the address into the FSR and then write to the INDF register. In the block diagram context, CPU and ALU. The FSR is often depicted connected to the CPU and the Arithmetic Logic Unit, ALU, showing its role in addressing and data manipulation. Data memory. The data memory block shows the general purpose registers, GPRs, and special function registers, SFRs. The FSR points to these memory locations during indirect addressing. Instruction decoder. The instruction decoder decodes the instructions that involve indirect addressing and manages the interaction between the FSR and the INDF. Benefits of using FSR. Flexibility allows for more flexible code, especially for repetitive tasks and operations on data structures. Efficiency reduces the need for multiple instructions to access different memory locations. Simplified code. Easier management of pointers and indices, particularly in loops and iterative processes. Summary. The FSR in the PIC16F684 is a powerful register that enhances the microcontroller's ability to handle data efficiently. By using the FSR to hold addresses and the INDF register to access data, the microcontroller can perform complex memory operations with simplicity and flexibility. The block diagram of the PIC16F684 places the FSR centrally in the architecture, highlighting its importance in the overall operation of the microcontroller. Next, let's look at the status register. What is it? What does it do? The status register in the PIC16F684. In this chip, the status register is a special function register, SFR, that plays a crucial role in the operation of the CPU and in every other PIC chip. It contains bits that reflect the current state of the processor, control the processor's operation, and provide information on the result of arithmetic operations. This register helps manage the microcontroller's behavior and affects how instructions are executed. Location in the block diagram. In the block diagram of this chip, the status register is typically depicted close to the arithmetic logic unit, ALU, and the CPU core. It interacts directly with the ALU and influences decision-making processes in the CPU. Components of the status register. The status register is an 8-bit register with each bit serving a specific purpose. Here are the typical bits in the status register and their functions. Carry bit, C bit, 0. Function. This bit is set when an arithmetic operation generates a carry out of the most significant bit. It's used to detect overflow in addition and subtraction operations. Usage. Important for multi-byte arithmetic operations. Digit carry bit, DC bit 1. Function. This bit is set when an operation generates a carry out of the 4th bit, low nibble of the byte. It's mainly used for binary coded decimal, BCD, arithmetic operations. Usage helps in BCD adjustments. 0 bit, the Z bit, bit 2. In Canada we say Z. Function. This bit is set when the result of an arithmetic or logic operation is 0. Usage. Commonly used in loops and conditional branching to check if a result is 0. Power down bit, PD, bit 3. Function. This bit indicates when the device is in sleep mode. It is cleared when the device wakes up from sleep. Usage. Used to check if the microcontroller was in sleep mode. Timeout bit, TO, bit 4. Function. This bit indicates if a watchdog timer reset has occurred. It is cleared by a watchdog timer reset and set by other resets. Usage. Used to determine the cause of a reset. RP0 and RP1 bits, RP0, RP1, bits 5 and 6. Function. These bits are used to select the bank of data memory, RAM, being accessed. The PIC16F684 has multiple banks of data memory, and these bits help in selecting the appropriate bank. Usage. Facilitates access to a larger memory space. Not used, bit 7. Function. Often bit 7 in the status register of the PIC16F684 is not used or reserved for future use. Functions and operations. Reflects arithmetic operations. After any arithmetic or logic operation, the status register bits C, DC, and Z are updated to reflect the outcome. For example, if an addition operation results in a value that causes a carry, the C bit is set. Controls CPU behavior. The status register directly influences the flow of the program. For example, the 0 bit, Z, is frequently used in conditional branch instructions like BTFSC, bit test, file, skip if clear, and BTFSS, bit test file skip if set, to determine the next instruction to execute. The RP0 and RP1 bits in the status register determine which bank of the data memory is currently accessible. This allows the microcontroller to handle more data than what can be addressed by a single bank. Example usage in code. Here is an example to illustrate how the status register bits are used. And I already showed that example in a video. Well, maybe I'll put the video in here. Alright, so here's some sample code which should help give an idea of what the status register does. Example usage in code. Here is an example to illustrate how the status register bits are used. Move LW 0x0f. Load W with 0x0f. Add a literal value to the working register. 0x01. Add 0x01 to the working register. Bit test file skip if set. BTFSS. Status, Z. Test 0 bit in status register. Go to no 0. There's a label here, no 0. Go to no 0. If 0 bit is not set, branch to no 0. So if it's not set, anyway, execution continues here if 0 bit is set. No 0, execution continues here if 0 bit is not set. I'm just thinking that maybe instead of this comment, there might be like more code written here and here, depending on what you're trying to do. Anyway, in this example, an addition is performed and the 0 bit Z in the status register is checked. Depending on whether the result is 0, the program branches to a different part of the code. Around 14 minutes and 50 seconds. Note to self. Summary. The status register in the PIC16F684 is a vital component that monitors and controls the state of the microcontroller. It provides flags for arithmetic operations, controls the CPU's mode, example sleep mode, and assists in managing the data memory banks. Its interaction with the ALU and its influence on instruction execution make it essential for efficient and effective microcontroller operation. Alright, well then, in the PIC16F684 block diagram, it shows instruction, decode, and control. What is this all about? In this chip, the instruction, decode, and control block is a crucial component responsible for interpreting and managing the execution of instructions fetched from program memory. Here's a detailed explanation of its function and importance. So what is instruction, decode, and control? Instruction decode. The process of converting the binary encoded instructions fetched from program memory into signals that control other parts of the microcontroller. Each instruction in the program memory is represented by a unique binary code. The instruction decoder translates this code into a set of control signals. Control unit. This generates the necessary control signals to orchestrate the operation of the CPU and other peripherals. The control unit ensures that the right data is moved to the right place at the right time. Functions of the instruction, decode, and control block. So I guess one of those functions would be fetching instructions. Instructions are fetched from program memory sequentially. The program counter holds the address of the next instruction to be executed. The fetched instruction is then passed to the instruction decode unit. Decoding instructions. The binary opcode of the instruction is decoded into control signals. These control signals determine the operation to be performed. Example, arithmetic operations, data transfer, branching. Generating control signals. Control signals manage various internal operations, including ALU operations, determine what kind of arithmetic or logical operations the ALU should perform, data memory access, control read and write operations to the data memory, register operations, manage data transfer between registers, peripheral control, interface with peripheral devices and manage their operations, managing instruction execution flow. Handles branching and conditional instructions, updates the program counter, PC, based on branch instructions, ensuring the correct sequence of instruction execution, interaction with other blocks in the block diagram, program memory. Some of these are headings. We're talking about the instruction decode and control, so this is under the heading program memory. The instruction decode and control block fetches instructions from the program memory, and in regards to the ALU, arithmetic logic unit, control signals generated by the instruction decode unit dictate the operations performed by the ALU. Example, addition, subtraction, bitwise operations. Data memory controls read-write operations to from the data memory, indirectly manages data memory access through registers like the FSR for indirect addressing, registers, manages the use of general purpose and special function registers, ensures data is correctly moved between CPU, registers, and memory. Example of instruction execution. Here's an example. Here's a simplified step-by-step example of how an instruction is processed. First, the fetch. The instruction at the address pointed to by the program counter is fetched from the program memory. Example, fetch the instruction move LW 0x34. Decode. The binary code of the fetched instruction is decoded. The move LW, move literal to WREG instruction is identified, and the literal value 0x34 is extracted. Execute. So I didn't include that example code on the screen, so it's confusing to you to hear that. Control signals are generated to execute the instruction. Load the literal value 0x34 into the WREG working register. The instruction execution updates the WREG with the new value. Update program counter. The PC is incremented to the point to the next instruction unless a branch instruction modifies it. Importance of the instruction decode and control block. Central coordination acts as the brain of the CPU, coordinating all activities based on the instructions. Efficient execution ensures that instructions are executed efficiently and correctly. Flexibility allows for the execution of a wide variety of instructions, providing flexibility in programming. Anyway, in summary, the instruction decode and control block in this chip is essential for the execution of instructions. It fetches instructions from program memory, decodes them into control signals, and coordinates the activities of the ALU, data memory, and registers to perform the desired operations. This block, meaning the instruction decode and control, this block ensures that the microcontroller operates correctly and efficiently, executing the program as intended.